I mean, it really did happen, but it's almost as if it didn't happen, right? It's,
What is that supposed to be?
huh? Do I recycle them?
Yeah, are you?
Yeah, yeah, but I took that picture years ago. A couple years ago. No. No, a couple years ago.
You're killing me.
All right. Yeah, it says on top of the green sheet if you need it there. Okay. All right, let's review some of the basic properties that we know and love. First, let's start with the definition of a logarithm. And when you're ready, we can do this problem too. If you've thought hard about the definition of logarithms before, then this maybe sounds familiar to you. There it is right there. The one thing I might ask you to stop and think about too, if you haven't thought about it yet, if you haven't thought deeply about it, is what about these restrictions? What's going on with B? Why is that restriction present, right? Like, why do we have to? It's an interesting requirement. B needs to be positive and not 1. Why? Have you thought about what happens if you break that rule? I mean, maybe there's something deep and dark and bad that happens. Always question the man. Why is that part of the definition? Yes. Like I said, random number generator. So I am giving you a note sheet that has this definition at the top. All right, so there it is. It's up at the top of your sheet. You don't need to write down anything today except for the examples that we have. Okay. All right. So let's get someone to rewrite this in. Right now, I might call it exponential form. So Claire, when you're ready, where is everybody now? I just moved seats. This is gonna throw me off. So could you rewrite this in log form? Right now, it's like written in the form something equals something to a power. How would you rewrite that in log form? Do you think you can take it? How would you do that? That is, I want a log in there somewhere. Log base what of what equals 1. Guys, Claire's thoughts. Log base what? M of something. Okay. Okay, agree? Agree? Yeah, in fact, this is just a rearrangement process. Let's just emphasize again that anytime you see this, you can write this. And anytime you see this, you can write this, right? There's just two ways of expressing the exact same information. And importantly, that's also why we write if and only if in between, right? These mean exactly the same thing, just expressed in slightly different ways. The other thing to say is that this shows forth that these are inverse functions, right? Yeah.
Like if B.
Oh, why can't B be 1?
Like couldn't B and X just if B was 1, couldn't X just always?
So the reason for these restrictions is that we'd like the log base B of X to be a proper function, and we'd like it to have the domain 0 to infinity. Yeah?
Oh, so like if it's 1, then it's just like
Yeah.
1, 1, 1, 1.
Well, no. If it's 1,
Oh wait, no,
then what? Yeah, what is the log base 1? There's only like one number that even makes sense in there for me, right? But like as soon as I start putting X values in here, I'm like, sorry, can't do it, right? What's the log base 1 of 5? I don't know either. Yeah. Okay. So that's why B can't be, again, we want this to be a function of X, and we want it to take all positive reals as input. And the other things won't allow that all to happen. So think through, that's good. I'm glad you actually did what I asked and like thought about that. That was good. Thank you. Keep in mind that the thing we get here, if someone asks you, what does this log evaluate to? The answer is whatever the exponent is, right? So it's underneath my writing up there now, but there's a reminder that if you really want a really simple definition of logarithms, you might just say that logs are exponents, right? Which some of you from last year might remember. Okay. The next set of properties there, I don't have like a full, there's not like, in fact, I don't know, there's not really even a proof to do. The proof is just directly from the definition for these properties for the most part, right? Like, why is the log base b of 1 equal to 0? Well, it follows from the fact that b to the 0 equals 1, and it's just rewritten in log form, right? And why is b to the 0 1? Well, I assume you thought about that back in Algebra 1, but if you need to like prove your exponent rules, then you and I can have a conversation sometime. But if we agree to this, then this definitely has to be true. Likewise, if we agree to this, b to the first equals b, well then this has to be the case, right? These last two are maybe a little harder to justify. Let me just say one or two things about that. Sometimes people call the last two properties the inverse properties, because if you have the functions, b to the x and log base b to the x, those two functions are inverses of each other, okay, by definition. And if you compose them one with the other in either way, that is f of g of x or g of f of x, if they really are inverses, what do you get? Well, in both cases you'll get x, or here I have y, I guess, whatever, doesn't matter. That is, if you put b to the y into log base b, you just recover y, don't you? And down here, same thing. If you have put log base b of y into b to the whatever, then you recover y. The intuition there, though, is not bad, right? If I ask you, remember the question that Cheyenne was kind of illustrating earlier, what are we doing when we evaluate this? We're asking what power turns b into b to the y. Well, when we ask it that way, it's almost not even worth asking, right? It becomes so clear. What power do I have to raise b to get b to the y? Well, clearly y, right? Isn't that the power I have to put on b in order to get b to the y? It's not even worth talking about in that form. This one's a little maybe harder to say out loud, but let's see if we can do it. Remember that logs are exponents, yes? Okay. So what is this then? What is log base b of y? Well, it's an exponent, and what job does it do? It lives to do what? It lives to turn b's into y's. Isn't that what this does? Isn't the exponent that turns b into y? Well, what happens when you raise b to that power? Well, naturally, you get y, right? So that should also make sense too. I just want to say those two things because a lot of people are like, well, did they cancel out? Okay. That's not very illuminating to me, right? Like, I'd really like to think about why that makes sense. Okay. Anyway, so these all do just follow immediately from the definition, though. So there's not really any proof to do, per se. There's no proof of these things. These are just conventions that mathematicians have agreed on. And in fact, mathematicians haven't really even agreed on them. Once you get to college, whenever you write log x, almost universally in college, they mean natural log because that's what we're using more often. But anyway, for at least in high school and on your calculator, this is the convention. I think you've used them before, haven't you? It shouldn't be new to you, I don't think. It's written on your paper. Let's try a few more problems. All right, we want to add in this. We want to add in some of the properties from the last page. And we want to just step it up just in general one notch or two, okay? The warm-up was the warm-up, right? But this is, we're trying to get back in our stride here now. By the way, be careful. There's a lot of, you don't want to start a bias, okay? With all the, with all the law,
Why is that not the fun of the day?
This should be the joke of the day. Go ahead and, I'll give you a couple minutes to do these, honestly, because I think these are all interesting. The last three especially are a little dicey. Give them a try.
You're so funny.
shows you how much I don't know. Like she used to be like, I don't know. She used to have what is this? Yeah, I've been putting that in, but it's not the word.
You're not a bracket. No, a negative. My brother stuck on my contact.
Kathy, you done? You done with things? Mostly done?
No way. She never wrote code. I have no shape.
Here, are you done? You guys done? Is this seating arrangement going to work? Alright, show me that this is a good seating arrangement, but the way you work. Yeah, how are we doing on those last three? Yeah? Yeah, maybe kind of.
Okay, so
Why? You're not talking to me variables. You have to totally dig the hole first.
All right, let me hear from a couple of you guys on the first ones at least. Okay. I'll call volunteers on the first six, and then I'll call on some people for the first six, and then I'll ask for volunteers in the last three if you have them. Listen, please. Okay. After each person gives their answer, again, please give a chorus of agree only if you agree. Okay. Michelle, are you able to give us the answer to the first one there? Where are you, Michelle? 2?
Yeah.
Agree? You guys, let's do this. Say agree. Say the word agree. Agree. All right, good job. All right. They're feeling the love there, Michelle. Good job. Corinne. What about B? Where's Corinne? She's not here today. She is going to sit there though. Robin. Did you hear her answer? 1/2? Agree? Okay. Proceed. Crystal. 2.37? Say it like you mean it.
Yeah.
Okay. We'll just assume she's right. D. Kevin. Where are you, Kevin? All right. Sorry, I got it. What'd you say? 5/2? Agree. Okay. For E, Gabe. Say it one more time. -1/3? Agree. That's a little bit of a headache there to get that, but I think I agree. Got the negative reciprocal. Okay, all right, I think I got that. Tricky. Daniel, over here. -3. Agree. Come on, give him some love. All right, good. Now, great. You want G? Someone want G? You guys seem very excited about this. So go ahead. 3n? Agree? Okay. Are you prepared to give some reasoning about that too? No? I need some reasoning on anything at all ever that I do in mathematics. Because I hear I like 3. My only thought, if I'm a confused person, is I see how you got 3. Like 5⁻³ is 125. I feel that. But is it like, okay, then does that mean the answer is 3 to the n? 3n? 3 plus n? Like how do I reason there? I think you're right, but I need some reasoning. Are you offering, Jasper? Some reasoning? Hey guys, I want to make sure everyone hears this.
For example,
Uh-huh.
like a way to describe it. For example, 2 to the 6 is 64.
Good.
Put off to 8 to the second times 2, which is 2 to the third.
Wait, guys, I want to hear this. Here, so 2 to the 6 can be written as.
Written as 8 to the second, which would be 2 to the third, and times 2.
Okay. Okay. Yeah. I like the intuition there behind that example that you chose. That was good. Yeah, I think I'm convinced that it's 3n. I don't know. Anyone have another thing to say about that? Why it's 3n? I don't know. You want to explain something? Oh, you're saying like rewrite the problem before we evaluate it? It's like log base 5 of 5 to the 3n? Do you feel what he's saying? Does that make sense? This is, in fact, just using properties of exponents from Algebra 1. This is the same argument, right? He still hasn't changed the inside. 125 to the n is the same as 5 to the 3n. And then it's clear, if, again, using the same kind of logic we use, this is one of the properties, right? 5 to what power gives you 5 to the 3n? Well, clearly now it's clear it's 3n, isn't it? It does the job. In fact, that suggests an interesting technique on these. If you can do a rewrite on the argument of your log, if you can do a rewrite and keep rewriting it to the point where finally you have whatever the base is raised to a power, then you're basically done, right? So if you can kind of figure out a way to rewrite and rearrange the input to the log so that it's the power of the base of the log, then you're done. It's just the exponent you have. That might be helpful, especially as we think about I, for example. Who has H? You want to talk about H? Yeah, go ahead. Go ahead.
Okay, so for my answer, I got e to the 4th times ln 4 equals 2 to the 6, because I noticed that like if you rewrite the log, it equals e to the ln 4 to the 4th. And since ln and e like have the same base,
Okay.
I
guess the only thing I'm wondering about is like, why is 4 ln 4 the same thing as ln of 4 to the 4th? Is that like a?
It's a log rule.
That's a log rule?
Yeah.
I don't know it. Do you want to either prove it right now or not use it? Which one? You can prove? Oh, you don't have to. I'm just pushing you on it a little bit. I'd love to hear if you can, or maybe because we don't have that property necessarily. I mean, we haven't talked about it yet. At least. Could you do it without that property? Is there a way to do that? I think you can, but how would you do that? You don't want to. Were you going to explain it the same way, Daniel? No?
Yeah.
With the way that Crystal did? I mean, I think a lot of you maybe remember that property. It is a property, but we haven't like talked about why that's true. We want to make sure that we understand it. Is there anything you can do with properties of exponents, just from Algebra 1 style? I think the answer is 4 to the 4th in the end, but I don't know why. I'd rather not use any like black boxes. The fact that this is a product of two exponents up in the power there is a situation in Algebra 1 where I was like multiplying exponents. I'm trying to think, when does that happen? Yeah. Yeah, one rewrite on this, I don't know if it's helpful or not, would be e to the 4th to the ln4. Do you agree?
Yeah.
Or
you could also do.
I'm loving it already. What do you? Go ahead.
E stop. E to the stop. E to the ln4 to the 4th, which would make it 4 to the 4th because of the property of because of the one that's like e to the log d of y equals y.
Yeah.
So we know e to the power of ln4 equals 4, and then we just put that.
Do you guys agree on the first step, the rewrite there?
Yeah.
By properties of exponents, isn't what we do with the power of a power, we multiply? And again, you should push on that too. If you're like, wait, hold up, justify that, you're absolutely right. But I just assume that everyone has already like explained that back in Algebra 1 and you've already like proved that. That x to the a to the b is x to the ab, right? Yeah? So that's the property she's using to rewrite this, isn't it? You multiply the exponents, you get 4 ln 4 as the exponent, right? All right, how are we doing the last one?
Terrible.
It is messy. Now I will warn you. I'm gonna push back if you try to use a property I've never heard of. Okay, Grant. So, what was your strategy? How'd you get it? Yeah, I like that. So, can you want to just write it up on the board? Your work. And as many steps as you possibly can. Give us like the whole thought process. You understand what I mean? All right, hey guys, let's give the play-by-play like it's a major sporting event, okay?
All right, Grant starts writing.
All right.
Grant starts writing the equation.
He's copied the problem on the board. Let's see what the next move is. He needs to stretch his neck just a little bit. Make sure he's in the mindset. He's about to write something. We're all waiting with bated breath. He just came out of a rough postseason. He's coming off an injury. And he still looks like he's coming out strong, though.
As many steps as possible.
8 to the 1/4. The crowd goes wild. 8 to the 1/4 is, in fact, the fourth root of 8. That's true. What's he going to do next?
Mr. Chase, can you make a commentary for the football games?
I'm trying to get as many.
I don't really know anything about football. All right, wait, hold on. Everybody slow down here. He just wrote 8 as a power of 4. Did he do that correctly? That's 4 to the 3 halves in there?
Yeah.
Woo! He's got some moves, guys. What's his goal? Do you see what's in his mind, audience? He's trying to get stalling. He's trying to get the inside of this inside the parentheses as a power of 4, isn't he? Because once he knows. Well, actually, I did that too.
Okay, you know what?
No. This is good. Now he's writing 32 as a power of 4. How did he do that? It's 4 to the 5 halves. Keep going. So now he has 4 to the whatever over 4 to the whatever. I feel where this is going. I feel like we're closing in. The nails are almost in the coffin. He has a fraction. This is it. He might trip. He might fumble. He might drop the ball on the fraction. Word. Let's see if he comes out clean. That's negative 17/8. I guess we're trusting him. And then it's clear that it's negative 17/8. And he drops the marker, and the game is over. Woo! We'll get a post-game interview in the locker room. Okay. All right. So that was some good moves. It looked different for everyone who did it, probably. Some people said, "Hey, I did everything in terms of 2s," and then maybe at the very last minute thought about what 4 would have to do for me. That's kind of how I thought about it. Yeah. But in the end, the answer is negative 17/8. No calculators required. Okay. That was intense. Do you agree? Right. So, there are a couple properties that you might remember that you've been trying to use. But before you use them, I insist that you prove them. Okay? I really do think that some of you were given these properties at some point in your Algebra 2 life, and no one told you why they work. They're just like black boxes. At any given time, like for instance, I always find this to be true with my Algebra 1, Algebra 2 students that I see, right? They're like, I can't remember properties of exponents. Do I, like, in this situation, do I multiply? Or do I add the exponents? What do I do? And you know, if you're a mature math student, that you shouldn't be memorizing those properties, right? They should just make sense from first principles. Am I right? Well, similarly, I think a lot of people try to struggle to remember these properties, but it's going to be really helpful, I think, to all of us if you can actually prove them in your moment of need in life. If we can actually prove these, okay? So let's do. Well, let me just let you struggle for just a minute on number 1 and 2 here, and then I'd like to see how you do. The boxes, guys, I apologize. The boxes are very small. So the boxes are meant to be bigger. So imagine that they are. And you'll need the table. You'll need the table at the bottom maybe for number 2. Like I said, as you do number 2, there's a table at the bottom.
You know what? Is it supposed to die with Mike and Daisy?
Yeah, so he's thinking 32 is 2 to the So 4 is the bottom.
I'm actually
Is the first one five?
Oh, true. Thanks, Sam.
Oh, what is this? That's not even what I said.
Oh, no, that's what this is.
All right, I've let you struggle for a minute, at least on number 1 and 2. Hopefully you guys are doing well. So what goes, excuse me, log, let's do, what is it, 3 and 5 for number 2? Is that what it is? Okay. So what is this? What goes there? What is it, log 3? Allow me to just write log 3. On your paper you wrote whatever it is, 0.477 or something. What's this one going to be? Log 5. We're looking for the exponent that turns 10 into 5. Well, a good name for that is log 5. Or you can look it up in your table and approximate it. So what's this exponent here? How'd you get that? You looked up this value in the table, you looked up this value in the table, and then what value goes here? And how'd you get that though? Okay, so if I don't have a table up here, I don't know what it is. But if I did have a table, I'd take the result of this and add that. Yeah? Yeah? And then what's the answer? What'd you get as your answer? It's whatever log 3 plus log 5 is, right? I mean, because now we're in this situation where we have log base 10 of 10 to the something. So I think that's the answer number 2. Now you can approximate this and say what it is too, right? But that clear thinking should help you in number 3 as you actually prove now with an A and a B, prove the product rule. You see how that's going to go? Replacement 3 is 5. Look at what I wrote.
Notice.
Think about how this appears in terms of how you wrote this.
Log 3. Log 3. That was funny. Which is log 3.
Once you're done with the product rule, prove the quotient rule. I think you'll find that the quotient rule proof is almost identical. And then the power rule one might be a little trickier. And if you're looking for a challenge that doesn't feel like these, maybe try proving the change of base formula too while you're at it. That's not on that sheet, but think if someone just has force-fed you that and you just kind of take that to be something you memorize, I don't know. You might need to think. You might need to think about how to prove that too. I just don't want to use anything in life unless I'm convinced that it's true. I'm not convinced by people just telling me. That's no good.
I guess.
All right, we are sadly very close to the bell right now. I would like you to, if you haven't finished the proofs, do try and finish those if you will. Your homework tonight, each homework along the way, has a few problems from the challenge problem as well. So those are just passed out. Just pay attention on each homework. You have a couple book problems, and then you have the challenge problems. The book problems are usually pretty easy. That's why I feel like you guys need something to, push you, stretch you, take you to the next level.